Today we're going to build an intuition for vectors, correlation matrices, and most importantly, eigenvectors and eigenvalues for principal component analysis or PCA. We actually discussed PCA before as a way to reduce dimensionality, and from the feedback for that video, I learned that there appears to be a bigger need to discuss linear algebra topics in depth. So in this episode, we'll make up for that and review PCA with a bigger emphasis on the linear algebra side and then focus on correlations rather than covariances this time. But some caveats. First, a reality check, especially if you're just starting in data science or analytics. Yes, linear algebra matters. You need to understand what the tools are doing and to make sense of the results. But beyond the fundamentals, you do not need to be a mathematician to do strong applied analytics work. If you work with tools like Excel, R, SPSS, eViews, or Python, for example, the software does most of the heavy lifting. Your real job is not to grind through the math by hand. It's to analyze, interpret, and make decisions from the output. That said, there's a catch. If you only know which buttons to press, you become dependent on the software and on whoever trained you. The moment you switch jobs, lose access to the same tools, or have to build something from scratch, you hit a wall. And that's why you still need the basics. You need enough understanding to adapt, to troubleshoot, and to move across tools, whether that means Excel, R, or Python. In my case, that's exactly why I built my teaching around Excel and my QuantProf Add-ins way back in 2002. Master the foundations first, and the jump to R or Python becomes much easier. And that has always been the philosophy of this channel. Learn the essentials, learn by doing, focus on the applications, and build skills that transfer across any software. So watching this video, know that this is the underlying thinking behind the educational content here. And with that, let's review our basic linear algebra applicable to PCA. And let's start with vectors. What are vectors? First, imagine drawing an arrow on a sheet of paper. That arrow tells you two things: which directions to go and how far to go. In math, that kind of arrow is called a vector. Now in 2D space, it will be defined by two numbers. Below are two such arrows defined by their two numbers each, 1, 1 and 3, 1. So the vectors 1, 1 and 3, 1 are plotted as shown here. 1, 1 means going 1 unit to the right, then going 1 unit up from 0, 0, depicted as the blue arrow. 3, 1 means going 3 units to the right, then going 1 unit up, depicted as the red arrow. Okay, now, what are matrices? You can think of a matrix as a little box of vectors. But those vectors aren't random. That little box of vectors becomes a machine that transforms any vector it encounters. Imagine a photo editing tool that can stretch, tilt, or rotate an entire image. Every point in the image moves according to the same rule. A matrix is like that photo editing app, except that instead of pixels, it acts on vectors in space. So let's have a matrix called A, defined as shown below, and let's multiply it to the blue vector 1, 1. And we have this. It turns out that matrix A is a machine that transforms the blue vector into the red vector. Almost always, two things happen to the vector when a matrix transforms it. Its length changes and its direction changes. The vector comes out pointing somewhere new, as shown in our transformation from 1, 1 to 3, 1. Now, let's use a different starting vector, 1, 0 instead of 1, 1. Now, something remarkable happens when we do this. Take a look at this one. One particular vector enters, it exits pointing in exactly the same direction, only longer. Here it is twice the old length, but the direction stays the same. It turns out that among all possible vectors, there are a few special ones. When these vectors pass through the matrix, they don't rotate, they don't bend, they don't change direction at all. They simply become longer or shorter. These special vectors are called eigenvectors. The word eigen comes from German and means own or characteristic. An eigenvector is a direction that naturally belongs to a matrix, It's a direction the matrix quote-unquote prefers, meaning it's the matrix's own direction or characteristic direction. So from the previous discussion, knowing the direction isn't enough. We also want to know how much the matrix stretches it. That amount is called the eigenvalue. Now check the equation below, where we have AV is equal to 2 times V. Note that AV is the same as a scalar number 2 multiplied by the same vector. In this case, the vector does not change. It only gets stretched by the scalar value, here by a scalar of 2. That was fairly obvious in our previous example, and this just formalizes it. So an eigenvector is a vector that belongs to or is associated with a matrix in a special way. When you apply the matrix to the vector, the result points in the same direction but just scaled by a number. That scaling factor is the corresponding eigenvalue. So here 1, 0 is the eigenvector and 2 is the eigenvalue, the amount by which the eigenvector gets scaled up or down without changing direction. In general, the formula looks like this: AV is equal to lambda V, where you use lambda as the scalar. But now we can read it almost like an English sentence. A matrix transforms a special vector into the very same vector, but this time multiplied only by a number instead of a matrix. That's all it says. The matrix A acts on the eigenvector, and the result is simply the original vector scaled by the eigenvalue called lambda. No change in direction, only a change in length. At this point, you might already have a hint at what we're getting at. If we work with covariance and correlation matrices, they will always have their own vectors, their own eigenvectors, that get stretched or contracted by an amount measured by the eigenvalue. So a 4x4 correlation matrix will generate its own 4 eigenvectors and 4 eigenvalues. A 10x10 correlation matrix will generate its own 10 eigenvectors and 10 eigenvalues, and so on and so forth. What is the implication of that? Remember that each eigenvector points to a unique direction in n space associated with the correlation matrix. And those directions never change, even after multiplying it by the correlation matrix. It also happens that each eigenvector is orthogonal or 90 degrees with each other. That means we can build an n-dimension coordinate system built along the lines of the eigenvectors. The problem here is that for us humans, it's hard to visualize 4D or 10D for that matter. So we'll just work with 2D space or two-dimensional space to work the intuition. We are now ready for the big reveal at this point. Knowing all the foregoing, we now state plainly that any given n by n covariance or correlation matrix can be broken down into n unique directions in n space, such directions forming the main axis in n space. In other words, an n by n correlation matrix will thus generate n principal axes in n space, the so-called principal components in principal component analysis. And that's it. That's what PCA attempts to do, to look for the coordinate system as defined by the eigenvectors associated with either a covariance or a correlation matrix. So a 3x3 correlation matrix will generate 3 eigenvectors that are the principal components in 3D space, with an associated 3 eigenvalues that say how much these eigenvectors get scaled up or down by the correlation matrix, but still maintaining the same directions in 3D space. This gives us a clue as to how PCA is actually used. We get and compare all the eigenvalues associated with each principal component, which tells us how much a particular correlation matrix gets scaled across these components, which then indicates how much principal components explain the correlations or covariance across the n dimensions. Now let's work with our old example, x versus y, plotted also below. And you can check out the video descriptions for the files. So here's the scatter plot. Now we're going to talk about covariance and then talk about correlations. Let's compute for the covariance first. As a way of review, we know that the covariance is written as the summation of x minus mu x times y minus mu y, all divided by n. Equation-wise, we can show it like this. Notice that it's always a pairwise computation, and we remove the centers from their variables and measure average co-movement of the two variables relative to their centers. The first interesting point is that if we measure covariance of a variable with itself, it simply becomes the variance of the variables. That is x minus mu x times x minus mu x, since it's with itself. The summation of that then divided by n. That's actually just the variance of x. Now, since we will be working with two variables only, we'll get a 2 by 2 covariance matrix to get all the pairings required. And let's take a look at this table to see what that looks like. By the way, we actually solved this before using the covariance matrix, but now we prefer using the correlation matrix to compute for the principal components. And listen up why that will be important. So correlation. Let's first review what's known as the z-score in statistics. That is, z is equal to x minus mu all over standard deviation. Now, it's important to understand what the z-score is saying. It measures how far a data point x is from its center mu divided by the standard deviation. That division by the standard deviation is a way of saying that we're measuring the distance between x and mu in units of standard deviation. That's it. That's what it means. Now, what's the impact of that? Well, if the original measurement might be in feet, liters, pounds, quarts, whatever. So x minus mu part will use that metric. But when we divide by the standard deviation, the denominator will also have that same metric as the numerator. That is, if x minus mu is in meters, so will the standard deviation be, also in meters. So dividing by the standard deviation produces a unitless measure, a measurement not found in the physical world. And what remains are only relative measures. That is, units of standard deviations. So imagine this, two sets of numbers where the second set is just a multiple of the first. And take a look at this. We'll also compute for the z-scores. Question, is 10 near its center at 6 as 100 is from its center at 60? Well, on an absolute basis, yes. 10 is 4 units away from 6, while 100 is 40 units from 60. But obviously, on a relative basis, they are exactly of the same relative distance. Well, how do you know? Intuitively, we know because set 2 is just a multiple of set 1. So they should have exactly the same relative distance. Statistically, we know because measured in standard deviations, 10 is 1.41 standard deviations away from its center at 6, while 100 is 1.41 standard deviations away from its center at 60. Get it? Okay, so where do we go from here? Well, that means in order to avoid the tyranny of absolute distances, we need to convert distance data into units of standard deviations. Rather than go through the whole process in a spreadsheet, let's just work on the intuition and start with the covariance formula, like so. Now, we already see that the numerator works with distance from center, so it becomes a matter of dividing by standard deviations to make the distance units relative, measured in units of standard deviation. Thus, we have x minus mu x all over standard deviation of x times y minus mu y all over standard deviation of y, then sum it all up and divide by n. So that gives you your covariance divided by standard deviation of x and standard deviation of y. And that's it. That's the correlation formula. And here, notice that we're already working with relative distances, working backwards from the formula. That is, we are already working with the data z-scores of each variable we are pairing. So in matrix form, this is what it would look like. So in tabular form, that'll be covar xx, covar yx, covar xy, covar yy. And again, the covariance of a variable with itself would be just the variance. So this is what it looks like in terms of the covariance matrix. And therefore, the correlation matrices would look like this. And notice that the diagonal for the correlation matrix is simply 1. Let's compute for the matrix from what we have so far. Please feel free again to check that video description for the values in the video. So we know that the covariance between x and y is 0.805. So we plug that into the matrix. We know the variances of x and y, so we plug those as well, and that completes the covariance matrix. The correlation matrix is much simpler because the diagonals are always 1 by definition. So we only have one value to plug into the matrix, and that's 0.763077, and shown here. Now, let's use the correlation matrix and compute for the eigenvectors using our QuantProf Excel Add-in with the output shown below. In general, we shall use software to compute the eigenvectors and eigenvalues, and we will generally not bother with computational methods for computing them. So here's the output from QuantProf. This 2 by 2 correlation matrix will have 2 eigenvectors and 2 eigenvalues. You can also check the equations to show that A multiplied by the eigenvectors will indeed give the value of the eigenvalue multiplied by the same eigenvectors. So this shows that the numbers are consistent. Now, we said before that the principal components define or delineate the coordinate system that is characteristic of a correlation matrix in this case. So let's plot that coordinate system given our original scatter plot. We know that the point 0.7071 and 0.7071 defines the vector that is principal component 1. Then we plot 0.7071 and negative 0.7071. That defines the second principal component, and we draw the resulting line as before. Just to note that the plot is not too precise here, as adjustments were manually made to the Excel scatter plot to make the intervals as equal as possible and even. But the point should be clear. So the points when projected along the first principal component explain most of the 1.763 all over 2 of the variations, or roughly 88% of the variations, estimated by using the eigenvalues. The second principal component explains the balance, or roughly 12% of the variations. Note that we are not regressing onto the principal components, only projecting the points. By that, we mean something like drawing a line onto a set of points and see how the shadows fall in line along the axis, as depicted in the charts. But why are we doing that? Well, we have to remember that PCA is about dimensionality reduction. We want to reduce the number of variables or factors if we have too many of them. Of course, the data we use here is rather simplistic, having just 2 variables, but the lessons we learn here can be extended to large data sets covering many variables. So back to 2D. If we were to drop one variable and go one-dimensional, which one should we drop? Well, we want to use the axis or principal component that explains most of the variability. Here, the one with the wider range, because it helps keep most of the informational content of the original dataset once we start dropping axis. That is, because we are dropping axis, we don't want to lose too much of the explained variation when we do so, to keep a high explanatory power with the remaining axis we have. So if we go from 2D to 1D, this boils down to which axis should we choose. Shown here. Based on these projections, clearly PC1 captures a bigger chunk of the variation. So intuitively, we like to keep PC1 as it captures much of the explained variation and then drop PC2. Alright, one final note. Notice that the principal component can be thought of as a rotation of the original coordinate system without changing the cloud of points in two-dimensional space. Think of all the points of the scatter plot as static horses in a merry-go-round. The merry-go-round can keep on turning and going around, moving all the points relative to the whole surrounding, but they're not really moving relative to each other as they remain fixed within the merry-go-round. That's how you can think of the cloud of points. Now, this will happen a lot with these kinds of rotation in PCA and factor analysis, where there will be a search for the best coordinate system in n space by force-fitting a coordinate system onto a cloud of points. We shall have more discussions about these kinds of rotations in the future. So, where do we go from here? Well, similar to the original conclusion in our previous video, we simply drop the y-axis and proceed with the regression between the remaining axis x and the dependent variable, the variable z in our case. And that's it. That's the dimension reduction we were looking for. So, some practical tips. With some statistical software, this will be GUI based, meaning you have a graphical user interface, and all you need to do is upload data, select from menus, and click on some stuff on screen and do all the analysis without doing all the above work shown here. Others might be code-based, like Python or R, but because of their extensive libraries, it is still a whole lot simpler and coding is minimal to do versus all the previous work we did above. So don't expect that in real life, we're going to be doing all that we outlined a while ago as is. We just did this to demonstrate the intuition and core ideas that a data analyst should keep in mind. For example, the advice to use the correlation matrix instead of the covariance matrix only makes sense if you understood the discussion we have about different units of measurements. Somebody who runs PCA might not understand the difference and make that kind of mistake if they are not careful. Alright, so there you go. These are the minimum learning outcomes you would need to understand the basics of PCA. And if you find this useful, kindly like and subscribe to help support the channel. More skill building videos are on their way, so stay tuned. Also, kindly visit my new coffee page if you'd like to support this channel with donations. It'll really go a long way to help this advocacy. So that's all for now, and see you next time.